Many years ago at our university lab, we used to have a seminar or a project which we were going to represent for the audience or the others. The thing that we have or we want to do is to make a mosquito repellent. We did use a taser and other mechanics for getting the mosquito into our device. The problem was that we did finish at the day of the presentation. We do not have any time to practice and to know what are or to think what the audience are going to ask us about. Although we continued at this day or at the day of the event when we were presenting for the others, the things were going really good. We even don't expect that. It was going good and good till someone came from the audience and asked us about about the part of the circuit, or which was the electronic part of the circuit. He asked us about the components of it and the mechanism of working it. The problem was that we did just use it and put it at our project because the time was very short. This thing put me and my friends at an age which if it is the right word. I was looking at my friends and they were looking at me. For few seconds, after a while, one of us starts to talk and the other continued it, and we just make it. I don't know how, but we did make it. This thing put us in a situation and a discussion about the situation we were in. We did thought that we have to know what we are doing. We have to know our circuits and we have to design them, not just to take them and put them at a new manufacturing way or a new technique way. We started from that point, and our friends and my friends also supported us on doing this. After that day, we started to search and dig for our technologies that is available, and we did seek for what the world were heading towards. We searched for many labs and work and many things until we find this thing. You did notice that the name of our slide is called memristor and memristor systems. This is an advanced thing or a new thing in electronic engineer. At this seminar we are going to present it and trying to describe a few things of it. Which we do have now at our screen is called an analog computer. This is the old stuff, which is the main brain of the computer, which was the analog processor. You have noticed that the problem is not the problem we are going to solve. The problem is the wires, as you are seeing. So it was not good for calculations. The thing we had problem is that we are nowadays using digital computers. The problem is that due to quantum physics, computers were heading towards to be more faster and smaller. This thing had end due to quantum physics. It cannot be more smaller than this. So we have to or the world should have to think differently to do this. They thought or about the old era where they were using analog computers or analog stuffs. 1971, a scientist called Leon Chua had stated that there were the four fundamental circuit elements which were called the memristor. This thing was the solution for our problem. The symbol you are noticing at the screen by the white thing at the center of it, it's called the memristor. Down at the figure down, you are noticing that there is the three fundamental circuits, which is the capacitor, the resistor, and the inductor, and the fourth new one is the memristor, as stated or described by Leon Chua at 1971. At 2008, this memristor were fabricated at Hewlett Packard Labs or HP Labs by a team of expertise. The thing which is the main principle of, or the main idea of the working principle, that the memristor is just a variable resistor which did change its resistance value by an electric field that is subjected to its two terminals. These electric fields do make the internal structure of the memristor to move forward and backward, changing its resistance. By doing this, it does saves the amount of the current that it has gone through it, and we can just take the source of the battery, and after a while we can read it again. This is type of a non-volatile devices. It's called a non-volatile devices, which is what we have here. As we did describe, the voltage and the current change the analog value. What you are noticing down at the center of the screen, that or at the slide, we have the materials that is building the memristor. This is a simple ones. We have a top electrode and a bottom electrode. Between them there is with a material which is the main material for which the doping starts at it, and the moving happened at this part. At the right we have the current versus voltage or IV curve of this device. Many of us can think that how this device can save the data, or how can we take the data out of it, or how can we store the data at it. Which we have noticed that it's a two-terminal device. The thing that we have is this device work on a low resist or a low voltage, which is from going from the positive to the negative voltage polarity. We have regions we used to when we are going to do something on it. When we are right, we have a different voltage values. When we are going to read, we have a voltage different values. The mechanism of that is due to Einstein's equations, or it just did break the Einstein's equations, which we have what we have now. The main thing we have to know that when we change the voltage from a low value to a high value, the barriers of the central part of the memristors, which is moving forward and backward, changes fast and slow. This velocity changes very fast and slow. according to the amount of the voltage that is supplied to it. We can put a voltage. This move go for a single millimeter or millimeter in 1,000 years. We can change the voltage and make it higher to make it go very fast for a meter, for example, in a second. This small thing help us in the way that we are when we were going to write and when we are going to read. You are noticing that there is regions at this IV curve for the write and 2 for the read, and there is this transition which is an selected part of it. What we have now here is it's called a crossbar or a memristor crossbar. You are noticing that all of these things are the memristors, but you notice that the symbol is just looking like a resistor because the memristor is simply a resistor which change its value by time due to the amount of the voltage or the electric charge that is subjected to it. What we have now is called the conductance, which is stated as G, which is 1 over R or 1 over the resistor. What we are seeing now is a model which have been built at known company. It is used for testing or for learning purposes. What you are now seeing is in the blue thing is the amount of the resistance at the memristors. This is a crossbar. By a simple way, all these blue dots are the memristor values or the memristor resistance. All of the orange things is the selected resistance or the thing that we operate or we are going to change its values. The main problem or the main thing that we have about the crossbar or that configuration is the sneak path current. This sneak path current make a very or take a very high power consumption. It would lead to a bad read margin and to sometimes a write failure. This sneak path current happens when the current goes at a different way, differ from the way that it should use, as you are seeing at the figure at the right side of the seminar slide. What we have now is how to solve this problem of the sneak path current. They use many techniques. They use 1T, 1R, 1 transistor and 1 memristor, that they put a transistor for each memristor in the crossbar. Other way, they are using a diode for each memristor of the crossbar. Other way are using selectors for each memristor in the crossbar. There is new ways to put one transistor for a row of memristors. This is called 1TNR. What we have now is a different technique way for solving this problem. We just apply a voltage to the cell that we are going to put voltage at it. This is a memristor. All of these things are the memristors. This is a memristor we are going to put the values or to put our values or to save it at it. We just subject it to a voltage. We put all the other memristor or the other cells or columns to half of this voltage. This thing helps us to solve the sneak path current issue or problem. This put us into low power consumption, lower than it was when we have that problem of the sneak pass current, but is still not the thing which is good for this technology. What we have now is a 3D model of the crossbar. All of these wires, or the top wires, is the top electrode, and this is the bottom electrode. This is the memristor device in the cross section of each top electrode and bottom electrode. What we are noting that this is a 3D model, so all of these things is memristors. We used this for a technology called a RAM memory, or a resistive random access memory. This thing, or this type of memory, is a non-volatile memory which depends on the memristor. It's a good thing, and is small types of memory and of non-volatile memory. It does it is located at the center of the center of the or the hierarchical diagram of the memory technologies. It is located at the center of it. What we have is we used the crossbar for something called a RAM memory. Now we are going to use it for calculations or for processors. This is called in-memory computing. We used the crossbar for many applications, which is called in-memory computers. You have you can just go and dig for what we meant by in-memory computing. When we collect two memristors by this mechanism, we have and apply a voltage. We at the first we save an amount of the current we have here and this resistor, and we apply another voltage for this memristor and for this memristor. Now we have amount of current which is going to go through this memristor and head down forward, and we have also another amount of a current which is going through this memristor and head down. What we have that what we did notice that we just make an addition of these two currents as the equations describe. We have an addition or an adder, as we are noticing. The thing that is, this is an analog adder because we apply a voltage or a current by a different way other than zeros and ones, by a different way. It is in the milliamps or in a nanoamps values. What we have now is a memristor crossbar. This memristor crossbar contains many memristors, as we are seeing now, from 1 to 4. All of these are memristors. Any memristors has its conductance value. We did not call it a resistance, we call it here a conductance, which is 1 over R or 1 over resistance. This conductance, when we are going to use this crossbar architecture, we can just apply many, or we can just put as we are seeing now, many values for the memristors. We program it with many values. After a while, we use these values, or when we apply certain voltages at a certain memristors, as we have now, we can apply it to this, and when we receive an current, as we are seeing now, We can also use the that crossbar for as a 3D model or a 3D structure, as we did use it for the RAM application for in-memory computing application also. The question is, why did we use this architecture, crossbar architecture, or memristor even? The main advantage of it, or the main benefit, is that it does saves the power. It does just consume a small amount of power, which is a main problem that scientists have, or main problem that the world is facing now. It also have small sizes. It from nanometers to micrometers, but the world is going forward a nanometer. Now they have reached a 1 nanometer memristor. The applications for this crossbar configuration, we can use it at the fourth industrial revolution. We can use it for machine learning, for accelerators, to solve many problems or many data problems, and we can use it for Internet of Things. The challenges which the scientists are facing is the amount of the ADCs, analog to digital converters, because for any single column which we used to have, we have to make an ADC if we want to just take it and manipulate it or change it to digital thing to make, because all of the world we are, or all of the technologies that we are dealing with, or most of it, is nowadays a digital. Main problems of the crossbar architecture or its application, that it cannot, or it may not replace the old NAND technology, because of it is slower at applications and faster at other applications.